All right, let's continue chapter 11 with section 1.4, the comparison test. So the comparison test. In the comparison test, the idea is to compare a given series with a series that is known to converge or diverge. For instance, let's look at this series. Okay, so we're looking at this infinite sum as n goes from 1 to infinity, described by this equation, right? So this reminds us it's very similar to this one, which is a little simpler. And that's usually the pattern you're going to see in this section that we're working with. We're going to be trying to establish whether a series is convergent or divergent. That's a little sort of complicated, and we want to think of something a little bit simpler that we know for sure is convergent or divergent. Very often it'll be geometric or p-series, and that'll make it easy for us to establish whether the one we want to work with will converge or diverge. Okay, so for example, a very common pattern is to think about the highest term both in the numerator and denominator. In this case, it's just 1 and 2 to the n. That brings us to this one. And this one is geometric, right? Notice that we can just take the this guy here. We have Riemann sum as n goes from 1 to infinity of 1 over 2 to the nth power. And we can easily rewrite that to the sum as n goes from 1 to infinity of 1 over 2 times 1 over 2 to the n minus 1 power. And that's geometric. Geometric with that constant equal to a half and r equal to a half. And so because the 1/2, the absolute value of r is less than 1, right, converges. Absolute value of r is less than 1. That means that this will converge. Good. And in this case, well, it's a half, so it works out. Okay. So we want to, so this one is geometric and it's convergent. So we want to establish how does it relate to the one we're actually working with, right? We want to see how that helps us determine or establish whether this converges or diverges. So we want to note that on a term-by-term basis, on a point-by-point basis, for any value of n, this is always true. That 1 over 2 to the nth plus 1 is always strictly less than 1 over 2 to the n, 2 to the n. So this shows that that on a point-by-point basis, the terms of this sequence are always going to be smaller than the terms of this sequence. And because we know, we've established that the sum from n equals to 1 to infinity of this one converges, we're going to see that that establishes that this also converges. They don't converge to the same thing, so we don't necessarily know what they converge to. We're just establishing that they converge. Okay, shows that okay, so they don't necessarily go to the same thing. Notice that because this is geometric, converges, and we know that this whole sum, because it's geometric, will converge to, remember this converges to a over 1 minus r, which in this case is just going to be equal to 1. So that's why we know that the sum from this guy, the sum of these will converge to 1. So therefore we know that the sum of 1 over 2 to the n plus 1, and then we want to compare that to the sum of 1 over 2 to the n as n goes from 1 to infinity. So we know this whole thing equals to 1, and we know that this must be less than that, right? Because on a term-by-term basis, each one is smaller. Good. So that's how we can conclude this guy over here. Notice that each one of the terms is positive, so as we're adding these guys, we're always adding some positive amount. This wouldn't be true if some other terms were negative, so this really only works for cases where they're all positive. Let's see if we can do like a visual of this thing. We have, let's go to Desmos, let's put a table format where we have okay, so here we have 2 to the nth power, 1 over 2 to the nth power, and 1 over 2 to the nth plus 1. So because the plus 1 makes the denominator just a little bit bigger, and that means that when I divide it, it makes it just a little bit smaller. So when n equals to 1, we see that the purple one is a little bit smaller than the green one. Good. So then if we keep going to the next term, second term, we can see that, again, the purple one is a little bit smaller than the green one, right? And then we do that same for the third term, and for the fourth term, and for the fifth term, and so on and so forth. So you can see that they're both getting smaller. They're both always smaller. They're both always positive values. They're both getting smaller and closer to 0. But on a term-by-term basis, it's always clear to see that the term of 1 over 2 to the nth power is always a little bit larger. The green one is always a little bit larger than the purple one. And in this case here, where it almost looks like they're the same, they're not. If we zoom in, we see that the green one is still larger than the purple one, right? So that's always the case. So then the argument becomes that if we know that the purple one is always a little bit smaller than the green one, and we know that if we add up all the green ones from 1 to infinity, we add up all those green ones and all those fractions, right? 1/2 plus 0.25 plus 1.25, right? If we add up all of these decimals forever, they add up to 1, right? We've established that. So then what about this sum, the sum of all of these decimals? Well, I don't know what they add up to, but they definitely add up to less than 1, right? That's what we want to conclude. Okay, so the inequality 1 over 2 to the n plus 1 is less than 1 over 2 to the n shows that our given series, the one we're working with, it has smaller terms than those in the geometric series, and therefore all of its partial sums are also smaller than 1, the sum of the geometric series. This means that its partial sums form a bounded increasing sequence, which is convergent. It also follows that the sum of the series is less than the sum of the geometric series. Okay. Similar reasoning can be used to prove the following test, which applies only to series whose terms are positive. The first part says that if we have a series whose terms are smaller than those of a known convergent series, then our series also is convergent. And the second part says that if we start with a series whose terms are larger than those of a known divergent series, then it too is divergent, right? So the comparison test. Suppose that the series A sub n and the series B sub n are series with positive terms, right? So each individual term is positive. Otherwise, this doesn't apply, right? All bets are off if we got some negatives in there. But if they're all positive, then we can establish this comparison test. So if the series B sub n is convergent and A sub n is always less than or equal to B sub n for all n, then we can conclude that the series of A sub n is also convergent, right? So notice the pattern that on a term by term, the A's are smaller than the B's, and the sum of the B's converges, therefore the sum of the A's also is convergent. On the other hand, if we know that the series of B sub n's is divergent, right? They add up to infinity, they keep growing and growing and growing. And we also know that A sub n is always greater than B sub n for all n, so the A's are always bigger than the B's, and the sum of the B's adds up to infinity, then we can conclude that the sum of the A's must also be divergent. Good. Okay, in using the comparison test, we must, of course, have some known series B sub n for the purposes of comparing. For most of the time, we use one of these guys. So these are very popular, very common for the exercises we work with. Keep an eye out for P series, something like this, 1 over n to the power of p, and we know this converges if p is strictly greater than 1, and diverges for p less than or equal to 1. Good. And also another common example is geometric series. So we know that in a geometric series it fits this form, and it is convergent if the absolute value of r is less than 1, and diverges if the absolute value of 1 is greater than or equal to 1. Okay, so these are just two popular series to compare our exercises with. So keep an eye out for that. So here's an example. Example 1, determine whether this series is convergent or divergent. Okay, so what we want to do is compare it to something. We want this something to be something that is much simpler, right? Ideally, and something that we can tell either converges or diverges, and we want to establish an inequality that is useful, right? Sort of in the right direction. Okay, so the pattern that we often follow is to think about the largest term for the numerator and denominator. So because there's only a 5 in the numerator, I'm just going to keep that 5. So I'm just going to say consider the series as n goes from 1 to infinity of 5 divided by 2n squared, right? Because it's the largest term in the denominator, the largest term in the numerator. So let's consider that guy right there. Okay, so on a term-by-term basis, I know that each term is positive. So note, each term of the series is positive. So note, each term of the series is positive, right? That's important, because if some of these terms were negatives, then this wouldn't apply. So also note that 2n squared is equal to 2n squared, of course. But now if I add extra terms to one side, then it must be true that 2n squared is smaller than 2n squared plus 4n plus 3, right? Because n is positive, so 4 times n is going to be positive, plus 3 is positive, so if we add a positive term to that side, it's going to end up being bigger. Good. And then when we flip it under 1, then 1 over 2 to the n squared, and 1 over 2n squared plus 4n plus 3, right? So if this denominator is bigger, it turns out that the fraction, when we flip it upside down, is going to be smaller, like this, right? Think of, for example, if we had 6 is less than 10, but then if we flip it over, then well, let's do. Think of like 5 is less than 10, but if we flip it over, then 1 over 5 is bigger than 1 over 10, right? 1 over 5 is 0.2, and 1/10 is 0.1. So that's definitely true. Okay, so when we flip it underneath 1, we get that. And now if we multiply both sides by 5, that doesn't affect anything. So that'll be 5 divided by 2n squared is greater than 5 over 2n squared plus 4n plus 3. Okay, so on a term-by-term basis, for each value of n, we've established that this one is always less than that one. Good? All right, so we have that part now. Now let's think about what this is. So note that this guy, from 1 to infinity, the series of this guy is equal to, okay, let's pull out the constant, 5 over 2, sum of n goes from 1 to infinity of 1 over n squared, and this is a p-series. with p equal to 2. And so we know it converges. Right? For p series, it converges whenever p is strictly greater than 1, which is true here. Okay? So we have that on a term-by-term basis. This one's always bigger than that one. And we have that this one converges. Therefore, the smaller one must also converge. So that means that this guy, from 1 to infinity, of 5 over 2n squared plus 4n plus 3 also converges. Converges by the comparison test. Let's see if we can visualize this a little bit better. Go back to good old Desmos. So let's see, we have okay, so here we have the original one we're working with. Let's just put all those purple ones, right? So here's all the individual values. When n equals to 1, we get 5 over 2 times 1 squared plus 4 times 1 plus 3. So when n equals to 1, the denominator is just equal to 5 ninths. 5 ninths gives you 0.555555. That's this value right here. Okay, and n equals to 2, we replace all those values here with a 2, and we end up with this decimal, and that gives you this one. Right, so we want to keep going, for 6, for 7, for 8, for 9, for 10. Okay, and then we're going to compare it to this one, 5 over 2 to the n squared. And so for each individual value of n, we see that this one's always bigger than that one. For when n equals to 1, we ended up with 2.5 as opposed to 0.5555. When n equals to 2, we get a 0.625, that's this one, as compared to 0.2631. It's this one right here. Okay, and so as we keep going, we see that the green one is always bigger than the purple one, right? The individual terms of this one are always larger than the individual terms of this one. And so if we happen to know that the sum of all these green ones, right, the sum of all of these decimals converges. Now we haven't established what they converge to, but we do know by the p-series test that they do converge. So because this converges to something, and the purple ones are always positive numbers, so they're always trapped between the x-axis and the green dots, right? We don't have a purple dot that's down here below the x-axis because it's never negative. All the purple ones are always positive, and they're always smaller than the green ones. And so if the sum of the green ones out to infinity converges, then it must be true that the sum of the purple ones also converges. We can also visualize this in terms of rectangles. If we can envision a rectangle that has a base of 1 and then a height equal to this, then the area of that rectangle would be the same as the height of the rectangle. And so we can turn it into a question about finding the sum of areas as opposed to finding a sum of an infinite summation of decimals. So let's see what that would look like. Okay, and so here's a nice little visual representation of that. So here we have the dots that represent this function, 5 over 2 to the n squared. And so if we create a little rectangle that has a width of 1, then we have a rectangle whose area is equal to the value of that rectangle at that point. So mainly in this case, it's the 2.5, right? So if we put a 1 here, we end up with a 5 over 2, which is a 2.5. And then when we put a 2 in there, we end up with 2 squared is 4 times 2 is 8. You get 5/8, which is equal to 0.625. And that's the height of the second rectangle. And so on and so forth. So here's just the first couple dozen of them, or just the first dozen. And as we can see, the areas are getting smaller and smaller and smaller and smaller and smaller. They're going to quickly converge down to 0. They're always positive, though. And by the p-series test, we know that the sum of all of these areas out to infinity is convergent. And so notice that in the center of each one of these rectangles, we have the value of the sequence we're working with, and it's always inside that rectangle, right? It's always positive, but smaller than this one. And so if I wanted to find the area of all the rectangles that represent that height, then we would be looking at these guys. The area of all of those guys. So as you can visually see, it's definitely going to be smaller, right? Because the heights are smaller. So if the sum of the larger ones converges, then the sum of all of these guys must also converge. All right, let's see what the author had as a solution. For large n, the dominant term in the denominator is 2 to the nth power, so we compare the given series with this series. So that's the inspiration for determining which series to compare it to. Okay, so now because this guy is bigger than that, the one on the right-hand side, this one is larger than that, and we know this one converges by the p-series test. Okay, so we know that this is equal to that, is convergent because of the p-series, and so it converges by the comparison test. Okay. Note 1, although the condition that a sub n is less than or equal to b sub n, or that a sub n is greater than b sub n in the comparison test is given for all n, we need verify only that it holds for n greater than some capital N, where n is some fixed number, because the convergence of a series is not affected by a finite number of terms, right? What is that saying? It's saying that for the first few numbers in a series, anything can happen. We could have values that are getting bigger, getting smaller, maybe even a few negatives. It doesn't matter as long as there exists some point, capital N, from which beyond that, everything works out well. They're all positive, they're all converging to 0, and we can do some sort of comparison to be able to establish what happens in the tail end, right? Because that's all that really matters. What happens as we go out to infinity. The first capital N of them don't really matter whether they add up to something really big, something really small, something negative. It doesn't matter as long as it's a finite number of those values, and then we can stop there and focus what happens beyond that. Good. Visually, we could say that if we have this, oops. So visually, we can have that if, for n equals to 1, we get that. For n equals to 2, we get that. For n equals to 3, we get that. For n equals to 4, we get that. Then we get that, and then we get that, and then we get that, right? It could be totally erratic, and like, what is happening? Initial set of, very erratic values. Maybe beyond this point, let's say that this is the point n, capital N. Beyond that point, everything works out the way we would expect it to. It begins to decrease toward, maybe from that point forward, all the values are positive, and they're decreasing, and then we can establish that maybe there exists some other sequence such that on a term-by-term basis, this other sequence is always a little bit bigger than the one we're working with. Always a little bit bigger. And if we can establish that the green one converges, then we've established that the blue one converges as well. Even though the blue one has initially had a bunch of crazy values over here, it doesn't matter. We can just add them up. They're finite, right? There's only capital N of them. This might add up to some huge number. These might add up to a negative number. It doesn't matter. They'll add up to something. They don't add up to infinity. They don't grow infinitely. They're finite. They're countable. So it's really just what happens at the tail end that matters. All right, so that's what that's trying to tell us. The terms of the series begin being tested must be smaller than those of the convergent series or larger than those of the divergent series. So the opposite doesn't help us, right? Meaning that if I'm trying to figure out what happens to the blue one, and let's say I'm trying to figure out what happens to this blue one, what happens to this blue one? I don't know. It seems to be doing this. What is happening there? Is that enough? Is it converging? And you find that you can compare it to something where maybe it's always a little smaller than this green one. And maybe here's the green one. It's true that the blue one is always smaller than the green one. But let's say that the green one just begins to do that. And so the sum of the green one diverges. Well, it does you no good to compare it to it. Okay, so it's always smaller and this one diverges. What does that mean about the blue one? It doesn't mean anything. It could be true that the blue one kind of follows it out like that. Maybe. Maybe the blue one also diverges. Or it might mean that perhaps the blue one begins to do this kind of thing. Maybe the blue one converges, right? We don't know. So if you establish that on a term-by-term basis, one of these is always larger and it diverges, it doesn't help us, right? Same is true for the opposite, that if we establish, we're trying to figure out what's going to happen with these blue ones. We're trying to figure out what's going to happen to these blue ones. And like, what's happening to these blue ones? I don't know what's happening. Maybe there they are. And you establish a comparison where we find that this new sequence of green ones is always smaller. Like maybe they look like this. Right? So it's always true that the blue one is a little larger than the green one. And we happen to know that the green one converges. Well, the green one converges. What does that mean about the blue? Well, it doesn't mean anything. Maybe the blue one follows it and begins to converge, right? Converge as well. Maybe. But maybe it's also true that the blue one takes off. Or maybe it's just consistent, right? Because if we get a constant value, then the sum of all these goes out to infinity. So maybe it diverges. Diverges. Okay? So you have to be careful what you compare it to. If you compare it to something where the new something is smaller, then it's helpful if that smaller one diverges. Right? So let's put these together in this little guy over here. There's 4 scenarios we want to focus on. There is, let's put little guys over here. This guy's over here. This guy's over here. Okay, so for the purposes of these, the blue one is always the one we're interested in, right? So in blue, the sum of a sub n is the question mark. Okay, so let's cover the good stuff. So the good stuff is that if, I'm trying to figure out what happens to these individual values of a sub n, what's happening to those, and I can figure out that there exists a new sequence. I know this sequence, and it's always true that the one I'm interested in is always a little bit smaller than this green one. On a term-by-term basis, it's always smaller than the green one, and the green one converges. Then I've proven that this one must also converge. So the blue one also converges. Okay? On the other hand, if we're like, okay, what do we do with this blue one? What's happening with this blue one? I don't know. What does it do? And we can find some new sequence that is always smaller than the one we're interested in. On a term-by-term basis, it's always smaller. And I know that this green one diverges, smaller than, on a term-by-term basis, always positive, but diverges. Now we can conclude that it must be the case that a sub n also diverges. Good. Okay, and then the ones that aren't helpful. If we are trying to figure out what happens to this sequence, and we compare it to, we find a new sequence where the new sequence is always larger than the one we're interested in, and then we know that this one diverges, well, then that doesn't help us with the one we're interested in. A sub n, who knows? Maybe it also diverges, maybe it converges. We don't know, right? It's not helpful. And finally, again, we're trying to figure out what happens to this blue one. Is it going to converge? Is it going to diverge? We don't know. I know, let's compare it to this one, where it's true on a term-by-term basis that the green one is always smaller than the blue one. And then we know that the green one converges. Okay, well, again, that doesn't help me. The blue one could converge, the blue one could diverge, we don't know. Right, so you have to be careful what you compare it to. Also, well, whenever we find this green sequence that we're going to compare it to, well, it would be helpful if that new sequence is something that we definitely know either converges or diverges. It wouldn't be helpful if we can establish that it can, something to compare it to, but then we don't know how to figure out whether that converges or diverges. So it'd be helpful if the thing we're comparing it to is something simpler and something that's easy for us to establish whether it converges or diverges. Ideally, will fall under either a geometric or a p-series kind of series. Okay, so here's an example where the comparison fails. So let's say we're trying to figure out what this is. All right, let's figure out whether this converges or diverges. And someone says, well, okay, let's compare it to this. Note that on a term-by-term basis, 2 to the n is equal to 2 to the n. And so 2 to the n minus 1 is always a little smaller than 2 to the n, right? And this is for n equal to 1 or 2 or 3 or 4, dot, 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 dot. Subtracting 1 is always going to make it a little bit smaller. So 1 over 2 to the n minus 1 is always going to make it a little bit larger than 1 over 2 to the n. Right? That's where we get this guy. So now we want to think about, well, okay, how does that compare to the sum as n goes from 1 to infinity of 1 over 2 to the n minus 1? And what is that, or how does that compare to the sum as 1 to infinity of 1 over 2 to the n? Okay, well, this guy is a geometric. This guy is a geometric, as we've seen before. This guy is equal to 1 to infinity of 1 over 2 to the n minus 1, where this is r equals to a half. And so we know it converges by it being a geometric. Converges. Okay, but this is bigger than that. So we haven't gotten anything valuable out of it, right? The smaller one, on a term-by-term basis, these are all smaller and it converges. So therefore, it doesn't really tell us anything about this one. This one might converge or it might diverge, right? So it fails to tell us anything useful up to that point. Let's look at that in the Desmos. Okay, so here we have a visual representation of the first few values of the sequence 1 over 2 to the nth power. So if we had all these little rectangles, base 1, and then we have a height equal to the value of it, here we are. So when n equals to 1, we have a half. When n equals to 2, we have 0.25, and so on and so forth, right? So we want to find the sum of all of these rectangles out to infinity. And so we know that the sum of all of these converges because this is a p-series. So by the p-series, geometric. This is geometric, so we know that all of them converge. And furthermore, we know that that they converge to 1, right? So this is a geometric, and they converge to 1. So then we want to ask ourselves, well, what about on a term-by-term basis, these guys, right? So when n equals to 1, it's way up here. When n equals to 1, the one we're working with ends up being up here, 1, and then the next term is 0.33, and then the one after that is 0.14, and then so on and so forth. So we can see that the purple one is always a little bit bigger than this one. Good. Now visually, it looks like maybe the sum of all the purple ones will kind of follow it into converging, but we haven't proven that yet, right? All we know is that the sum of the smaller ones is convergent. So now what about the sum of the larger ones? Well, we don't know. By this picture, it does seem like maybe they will converge. It does seem like it's going to follow it into converging, but we just haven't proven that yet, right? The comparison test doesn't give us that yet. We're not able to conclude that the series we're interested in converges by comparing it to this one. Okay. Nonetheless, we have the feeling that this ought to be convergent because it is very similar to the convergent geometric series, right? So as we saw, it seems like it does converge. We just haven't proven it yet. And so we can introduce this new test called the limit comparison test. The limit comparison test says that if we have two series, a sub n and b sub n, are both series of positive terms, and the limit as n goes to infinity of a sub n over b sub n equals to some constant c, where c is a finite number that's positive. That's important. It's a finite number that's positive. Then either both series converge or both series diverge, right? In other words, if you can find these two series, they're both positive series, and obviously you're going to want to introduce a new series that you either know for sure converges or diverges, just like before. And then if you divide them and apply the limit as n goes to infinity, and we get to some constant that's positive, this limit comparison test tells us that both will behave the same way. They will both converge or they will both diverge, right? That's what that's saying. The hardest part is really coming up with the new series to compare it to. Luckily, the same rule as before is usually going to work out. So let's say that we want to establish whether this converges or diverges. This is what we consider our a sub n. So this is the sum of a sub n, right? That's this guy. So we're going to consider a new one, b sub n. And, this is the hard part, but usually it works out to think about the largest term in the numerator, largest term in the denominator, 1 over 2 to the n. Okay, so we want to think about this guy. This guy I know is going to converge because it's a geometric, right? This converges. Well, again, geo, let's rewrite it. From 1 to infinity of 1/2 to the n minus 1 power. So it's geometric. We've seen this several times now. So it converges. Okay, so now we want to do the thing where we divide it. We want to find the limit as n goes to infinity of a sub n over b sub n, which will be the same thing as the limit as n goes to infinity of 1 over 2 to the n minus 1 divided by 1 over 2 to the nth power. That's pretty ugly. We want to simplify that as much as we can. So that'll be the limit as n goes to infinity of 1 over 2 to the n minus 1 times, and then the numerator times the reciprocal of the denominator gets me to 2 to the n over 1 like that. So then we just have one big happy fraction, the limit as n goes to infinity of 2 to the n divided by 2 to the n minus 1. And now we want to multiply the numerator and denominator by 1 over 2 to the n over 1 over 2 to the n. And we end up with the limit as n goes to infinity, the limit as n goes to infinity of 1 divided by 1 minus 1 over 2 to the n. Okay, there's probably an easier way we could have gotten to this level, but that's fine. So now when we apply our limit, then this will go to 0, and so the whole thing, the limit, equals to 1. Okay, so the limit comparison test indicated that if we find that the limit as n goes to infinity of a sub n over b sub n is a constant that's greater than 0, right, a positive constant, then both of these things behave the same way. They both converge or they both diverge. And since we already know that b sub n converges by the geometric, then by the limit comparison test, we've established that this one must also converge. So thus, by the limit comparison test, the sum of n goes from 1 to infinity of 1 over 2 to the n minus 1 converges. Okay, so this is the series we were working with. We had to come up with a new series to think of, to compare it to do the limit comparison test. That series is convergent by the geometric, because it's geometric. When we find this limit exists, and it's equal to a constant that's positive. So both will behave the same way, and so by the limit comparison test, we've established that this series also converges. See what your author did. This series converges or diverges. Use the limit comparison test. With a sub n equal to this guy, b sub n equal to this guy, the limit as a sub n over b sub n equals to this guy, equals that guy, equals that guy, equals that. Okay, that's the same thing I did. Since this limit exists and this is a convergent geometric, then the given series converges by the limit comparison test. Okay, so let's look at some examples from your book. Okay, here are your exercises from chapter 11, section 4. Let's just try a few of these. Let's, for instance, start with number 4. Okay, so number 4 says determine whether the series converges or diverges. And we have this guy, so let me copy it. Okay, so notice that n starts at 2 instead of 1. That's okay. So what do we want to compare it to? So it seems like the simplest thing to do is to compare it to 1 over root n. So note that if we have root n, well, that's equal to root n. But root n minus 1 must be smaller than root n. And that's for n equal to 2. Oops. That's equal to 2, 3, 4, 5, so on and so forth, right? Notice that it starts at 2. So starting at 2, that must be true. And then if we flip it over, 1 over root n minus 1 must be larger than 1 over root n, right? The smaller one, you divide it by the smaller, you get a larger number. Okay, and then what about this guy? So we've established that if this is, right, we've established that a sub n equals to 1 over root n minus 1, and b sub n equals to 1 over root n. We've established that a sub n is greater than b sub n on a term-by-term basis, on a number-by-number basis. But what about as we go out to infinity, what happens? Well, now if we consider the sum of the b sub n's, that's the sum as n goes from 2 to infinity of 1 over root n. Notice that this guy is the same thing as goes from 2 to infinity of 1 over n to the power of a half. And if this was a 1 here, it would be exactly equal to a p series. So it's just missing one term. But it doesn't really matter because for the p series, we know that this is going to diverge. And adding one extra term isn't going to make a difference. So this diverges by the P series. This is a P series with P equal to a half, so therefore it diverges. And if we come back over here, we see that on a term-by-term basis, each one of these is greater than that one. So therefore we establish then by the comparison test that this must also diverge, right? So by the comparison test, it must be true that the sum of the a sub n's, which was equal to the sum as n goes from 2 to infinity, of 1 over root n minus 1 also diverges. Let's look at this one on Desmos. Okay, so here we have a visual representation of our question. So the purple dots are the individual terms of the sequence we're interested in. The square root of n minus 1. Okay, so here's the one where n equals to 2, n equals to 3, 4, 5, 6, 7, and so on and so forth. So we want to know the sum of all of these guys out to infinity. And notice that they're all positive, and we can see that they're all getting smaller, so we can kind of maybe think that there's a chance that the sum of all of these individual values will converge to something, right? It meets the basic criteria. They're converging towards 0. Each individual term is getting smaller and smaller and growing towards 0. Therefore, perhaps it's possible that the sum adds up to something. However, then we compare it to this one, 1 over the square root of n, right? That's the height of each one of these guys for n equals to 2, n equals to 3, and so on and so forth. And then if we come up with these little rectangles where the base is 1 and the height is equal to its value, so in this first case it's equal to 0.7071, the next one is 0.577, and so on and so forth. And then we want to think about adding all of these. Well, because this is a p-series test, we know that this diverges. So even though they're getting smaller and smaller and smaller, that's not good enough. Not only do they have to grow towards 0, they have to grow there fast enough. If they don't grow there fast enough, then these areas are still not going to converge to some constant. So the sum of all these rectangles diverges, grows out to infinity. And as we can see on a point-by-point basis, the one we were interested in is always a little bit larger than the sum of all of these rectangles. So we can see that the one we're comparing it to, the terms they're all positive, they're getting smaller, they're growing towards 0, but that by itself is not good enough. This is a case where, despite that, the sum of all those areas still grows to infinity, still diverges. And the one we're working with, that would be this one, 1 over the square root of n minus 1. On a term-by-term basis, they're always a little bit larger. And so if the sum of the ones that are always smaller diverges, then it must be true that the sum of all the larger ones is also going to diverge. All right, let's try a different one. How about something like number 12? That looks nice and complicated. So let's see, does this converge or diverge? Let me copy it. Okay, so we want to find something to compare this with. And so if I start foiling out the numerator, even if I don't FOIL the whole thing out, I can see that the largest term in the numerator is going to be equal to 2k to the power of 3, right, if I start to FOIL it out. And in the denominator, the largest term is going to come from the product of this, which is going to be a k to the 4th power, times another k. I end up with k to the 5th power, right? If I FOIL this guy out, I'll end up with k to the 4th plus 8k squared plus 4k, 4 squared, which is 16. Right? And then if I then further distribute this, multiply this binomial times this trinomial, I'll end up with a k to the 5th power. Okay, so I'm thinking of this as this is like my a sub k values, and this is the one I want to compare it to, my b sub k, which then of course simplifies to just 2 over k squared, which is very useful because then that means that this converges by the p-series, right? So note that the sum of b sub k's as k goes from 1 to infinity is the sum as k goes from 1 to infinity of 2 over k squared. Let's pull out that constant, and then that'll be sum as k goes from 1 to infinity of 1 over k squared, which converges by the p-series test. Converges by the p-series with p equal to 2. Right? So that converges. Let's see if that's helpful. It might not be. Depends on the direction of the inequality. So now, how do we establish which one's larger, which one's smaller for these values? That's going to be kind of ugly. Okay, so how about if I go ahead and FOIL the whole thing out and then I divide them and see if the limit comparison test will help me. All right, let's see if the limit comparison test will help us then. So consider this. Consider the limit as n goes to infinity of as k goes to infinity of a sub k over b sub k, which is equal to the limit as k goes to infinity of the a sub k, which is equal to 2k minus 1 times k squared minus 1 divided by k plus 1 times k squared plus 4 squared times 1 over b sub k, which ends up being k squared over 2. Right? In other words, 1 over b sub k is equal to 1 over 2 divided by k squared. So multiply the numerator times the reciprocal of the denominator, we end up with that guy. Okay, so now let's see if this helps us out. This is going to be the limit as k goes to infinity of, let's FOIL out the numerator, 2k to the 3rd power minus 2k minus k squared plus 1 times k squared divided by k plus 1 times k to the 4th plus 8k squared plus 16 times 2 is the limit as k goes to infinity of 2k to the 5th power minus 2k to the 3rd power minus k to the 4th power plus k squared all over 2 times, and that'll be k to the 5th power plus 8k to the 3rd power plus 16k plus k to the 4th plus 8k squared plus 16. Okay, and so now the trick is going to be to introduce this new term that's going to be 1 over k squared, to the 5th power, divided by 1 over k to the 5th power, right? That's a new version of 1, as long as k is not equal to 0, which is not. And so now if I distribute those, I'll get the following. I'll get the limit as k goes from to infinity of the following: 2 minus 2 1 over k squared minus 1 over k plus 1 over k to the third power, then 2 times 1, or just 2, plus 16, and then 1 over k squared, plus 16 and 1 over k to the fourth power, plus, whoops, that's 16, that should be 32 here. And then 2 over 1 over k plus 32 over k squared times 1 over k to the fifth power. Okay, and so now if we apply the limit as k goes to infinity, that'll go to 0, 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 and that'll go to 0. So the whole thing will converge to just equal to 2, which is positive and greater than 0. By the limit comparison test, it must mean that both of these behave in the same way. They either both converge or they both diverge. And we've already established that this one is going to converge. Therefore, by the limit comparison test, we've established that this one also converges. Okay, so just to kind of sum it up, the limit as k goes to infinity of a sub k divided by b sub k equals to 1, which is a constant greater than 0. Also, we know that the sum of the b sub k's converges, and that was by the p series, Thus, we can conclude by the by the limit comparison test that the sum of the a sub k's, which was the sequence we're interested in, the sequence of 2k minus 1 times k squared minus 1 divided by k plus 1 times k squared plus 4 squared converges by the limit comparison test. As k goes from 1 to infinity, converges by the limit comparison test. Okay, note that we could have also done this exact same question by a straightforward application of the comparison test. You think about the following. So let me just copy it over here one more time. So we're working with 2k minus 1 and then k squared minus 1 all over k plus 1 and k squared plus 4 squared. And this is for k goes from 1 to infinity. So note that if I have 2k minus 1 being multiplied by k squared minus 1, that's always going to be smaller than just 2k times k squared, right? Subtracting 1, and this is where k equals to 1, 2, 3, 4, right? This is for k equals to 1 and 2 and 3 and 4 and dot, 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 dot. So this minus 1 here is going to make this term smaller than that term, and k squared minus 1 is smaller than that term. So we have a smaller times a smaller is always going to be smaller than the larger times a larger, right? On a piece by piece this one is smaller than this one. This one's the larger, right, because of the minus 1. And then this one is going to be smaller than this one. It's going to be the larger. So the smaller times the smaller has got to be less than the larger times the larger. Okay. Now, in the same spirit, we can look at the denominator now. If we have k plus 1, and then we have a k squared plus 4 squared, okay, and we want to compare that to, and this is going to be in the other direction, we'll have that k is always smaller than k plus 1, and we have that k squared is always going to be smaller than k squared plus 4 squared, right? Again, for k equals to 1, 2, 3, 4, 5, right? So it's kind of like on a term-by-term basis. So this one is going to be the smaller, and then this one's going to be the larger, right? So k is always smaller than k plus 1. And we have that this guy, k squared plus 4 squared, right, the whole thing squared, is always going to end up giving you a larger number than just having the k squared squared, right, without that plus 4. And so this will be the smaller. So again, we have the case that the smaller times the smaller is always going to be less than the larger times the larger. Okay? All right, so now if we think about this division and we want to compare it to, think about what happens as we compare 2k minus 1 times k squared minus 1 divided by k plus 1 times k squared plus 4 squared, and we want to compare it to 2k times k squared, and we want to compare the denominator with k times k squared squared. Okay, in the numerators, we know that this one is going to be smaller and this is going to be larger. So we know that this one is the smaller, just comparing the numerators. This numerator is smaller than this numerator, just the numerators, right? This is the larger numerator. And then in the denominators, this guy is smaller compared to that one, right? This is the larger. Just comparing denominators, larger, and this is the smaller. And remember that in a fraction, when you divide by an even smaller number, the whole output is going to be even larger, right? So think of like some comparisons here. If I had 7 is definitely smaller than 10, and then I'm dividing this one by, say, 3, and then I'm dividing this by something even smaller, like a 2, then clearly this answer is going to be bigger than that one. Right? Okay, so that's what we want to conclude here, that this must be smaller than this one. These two, right, this one's smaller than that one, so I already have that. And then I'm going to divide by something smaller on the right-hand side, something larger on the left-hand side here. So clearly this fraction is going to be even smaller than that one. Right? If I have something like 13 is less than 20, right? Okay, that's true. And then I'm going to come in and divide both of them by the same thing. Let's say I divide both of them by 5, then I keep the inequality. But let's say that, in fact, I divide this one by something even smaller than 5. I divide it by 2. Then it's just going to further help you to make this even bigger. So it still makes it true. Good. Okay, so hopefully all of that convinces you that the following is true. That if we have b sub n equal to 2k minus 1, and then k squared minus 1 over k plus 1 times k squared plus 4 to the second power, and we have some b, sorry, this is k, this is a sub k, sorry, this is going to be some a sub k value, and we have some newfound b sub k value, which is equal to this. That would be 2k times k squared all over k times k squared quantity squared. Okay, well then this guy reduces. B sub k, that's going to be equal to 2k to the third power divided by k to the fifth power, which then further reduces to 2 over k squared. Okay, well, we already have the inequality the way we need it. So if we can just establish that this converges, which it does, we've already talked about how that converges. It converges by the p-series. Therefore, we can use the comparison test to establish that this one is also going to converge. Right, so then the sum as k goes from 1 to infinity of b sub k is equal to the sum as k goes from 1 to infinity of 2 over k squared, which is equal to 2 times the sum as k goes from 1 to infinity of 1 over k squared. This converges by the p-series. So we can conclude by the comparison test. So by the comparison test, we can conclude that the one we were interested in figuring out, a sub k, as k goes from 1 to infinity, which is the same thing as this guy, converges by the comparison test. Okay, so here's a case where both the limit comparison test or the regular comparison test would have solved it. You don't have to do both. Pick one, whichever comes to mind is fine. Whichever one you find, whichever one occurs to you to use first and you feel is easiest is fine. All right, let's do one more. How about number 24? N plus 3n. Okay, as usual, the tricky part is to find something to compare it to and use either the comparison test or the limit comparison test. So let's go through some logical steps here. Clearly, it must be true that 3 to the n is equal to 3 to the n. This is for n equals to 1, 2, 3, 4, dot, 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 dot. Okay, and so if I add an extra n on one side, 3 to the n, and we want to compare it to 3 to the n plus n, well, then it must be that this side is bigger. This is bigger than that side, for n goes from 1, 2, 3, 4. Okay. So now 3 to the n plus n, and let's say let me erase this thing here. I want to figure out what the relationship is, but okay, so this one's the larger one, and I take the larger one, well, let's say for a second there that I divide them by the same thing. If I divide them both by the same quantity, which is equal to, say, 2 to the n, and divide this one by 2 to the n, well, then I maintain this, right? As long as they're both positive. The only way that the direction of the inequality would change is if I was dividing both of them by a negative number. But I'm dividing them both by the same thing, so it must be true that this is maintained. Okay? But then, even further than that, what if I divide the larger one by something that's even smaller? excuse me, by something that's even larger. So let's say that this one is like this. Still maintain them, right? They're both the same thing. And this one is going to be less than 3 to the n plus n. Wait, I've already created this thing. No, that's not what I want. Okay, but then if we want to go even further, if I take the same thing, the 3 to the n, and divide it by 2 to the n plus something that's even bigger than n, then I'm going to get a new fraction value that's even smaller. So I want to say that this is true. Right? So on a sort of a term-by-term basis, because this guy is bigger than n, because 2 to the n is larger than n, it must be true that adding this term to this denominator makes this whole denominator larger than when you just add an n to it. Good. And as you make the denominator larger, then the whole fraction gets smaller. Good. All right, so we can combine these things together and say that 3 to the n divided by 2 to the n plus another 2 to the n is definitely smaller than 3 to the n plus n divided by 2 to the n plus n. And now we can combine those guys and say that this is 3 to the n over twice 2 to the n. That's less than 3 to the n plus n over 2 to the n plus n. And so we can simplify this to be 1/2 times 3 over 2 to the power of n is smaller than 3 to the n plus n divided by 2 to the n plus n. Good. And now this is a geometric, right? The sum as n goes from 1 to infinity of 1/2 3 over 2 to the n power. Well, we can factor out the 1/2. That's 1/2 as n goes from 1 to infinity of 3 over 2 times 3 over 2 to the power of n minus 1. And this is a geometric. Where r equals to 3 over 2, that's equal to 1.5. That's larger than 1. So from geometrics, we know that this series diverges. So this diverges. So we know that on a term-by-term basis, this one is always smaller than this one, the one we want to work with. And we know that this sum diverges, so by the comparison test, we can conclude that this one must also diverge. Good. So we've established that if b sub n is equal to 1/2 3 over 2 to the n, and a sub n is equal to 3 to the n plus n over 2 to the n plus n. On a term-by-term basis, we've established that b sub n is less than a sub n, but we've also established that the sum of all of these guys, the sum of the b sub n's, diverges. So by the comparison test, we can conclude that the sum of the ones we were interested in also diverges. Okay, so that should give you enough to get started on your homework.